Hey everybody, I had to punt. I didn't have my PowerPoint here at the house, so I had to run around and make do and figure out how to make this go. So here we are, I'm ready, and you should have your foldable out and ready to fill in. So the first law we're going to talk about today is Dalton's law of partial pressure. It's super easy. So basically what he said is if I have a container of air, here's my container. That air has a whole lot of different gases in it. You should know that the most prominent gas that makes up air is nitrogen. And then there's a little bit of oxygen, even less argon, and just some trace other gases that are also in that container. So the overall pressure of the air is a combined effort of the pressure of the oxygen plus the pressure of the nitrogen plus the argon, the water vapor, and the carbon dioxide. So he basically said the pressure of a mixture of gases equal to the sum of all of the partial pressures of the component gases. So our formula ends up being P total equals P1 plus P2 plus P3. So you need to write that formula on the outside flap. When you open it up on the inside, it has an example problem already filled out for you. And this one says a balloon is filled with air. And they're only talking about this time the oxygen, the carbon dioxide, and the nitrogen. It's telling you that it has a pressure of 1.3 atmospheres. That pressure is that is your P total. So they're telling you what the entire balloon is filled with. And then it says if the pressure of the oxygen is 0.4 atmospheres and the pressure of the carbon dioxide is 0.3 atmospheres, what's the partial pressure going to be of the nitrogen? So they gave us the total and they gave us two of the parts. All you have to do is figure out the third part. Super simple. So if you take a look at what I did here, I wrote my formula because you know I'm a formula crazy person. And so I wrote my formula and then I actually plugged in my component gases. I don't care which version you do, this one or this one. I would probably lean towards this one because it's a little more specific with our three component gases. So the pressure total is equal to 1.3 atmospheres. So that's already been plugged in for you. And then they told us the oxygen pressure, which was 0.4, and the pressure of the carbon dioxide is 0.3. So all we have to do is isolate our variable, which is the partial pressure of the nitrogen. You know how to do this. Combine like terms. Since these units match, atmospheres and atmospheres, you are allowed to combine those. So it becomes 0.7 atmospheres plus the partial pressure of the nitrogen is equal to 1.3 atmospheres. So again, we want to isolate our variable, and the 0.7 should not be on the same side as the pressure of the nitrogen. So in order to get rid of it, because of the plus sign right here, we have to subtract. And most of you already knew that because you have some common sense. So we're going to get rid of that 0.7, and we're going to come up with the partial pressure of the nitrogen is 0.6 atmospheres. You can always go back in, plug it in, make sure that it equals 1.3 at the end. Unfortunately, you're going to hurt me, but I want to see this, okay? Because if you make a mistake, I can point it out easily. If you get the wrong answer and you show me nothing, I can't help you. All right, so that is Dalton's law. Super easy. Next, we've got Boyle's law. And so, you know, I come up with all these weird little things to say to kids so they can remember what is what. So what I tell kids usually is we are going to vote for Boyle for vice president. So Boyle for VP. So those are the two variables, pressure and volume, that Boyle figured out the mathematical relationship between. So it goes like this, at a constant temperature. So that means temperature is not a factor. The volume of the gas varies, here's a new word for you, inversely with the pressure. Now remember we talked about your little brother's head last week. We said if this was your little brother's head or a balloon and we added pressure to the balloon, what was going to happen to the volume? His head would shrink and his brain would leak out of his ears. And so we said when the pressure went up, the volume went down. I might write that somewhere, okay, because that's going to be very important to you. On the outside of your foldable, if you would please write down this formula. This is Boyle's law. P1V1 equals P2V2. And do not write this part. It will just confuse you. They're basically saying the temperature doesn't change. So if the temperature 1 was 23 degrees, the temperature 2 is also 23 degrees. So they're going to cancel each other out in the formula. So why even bother writing them? If you look at my hokey little picture over here, basically it's showing you two containers, and they are at different pressures. There's a little pressure gauge right over here. So here's your pressure gauge saying that the pressure was this and then the pressure changed. When the pressure changed, it was because the volume got smaller. And what we talked about last week is those particles are closer together, and so they're bumping into each other more often, making more collisions. And basically pressure is the number of collisions. And so this is your thermometer, and it didn't change, and so therefore the temperature is constant. Here's a graph. When we say that the relationship for Boyle's law is inverse, okay, that's a really big deal. That just means that one of the values is going to go up while the other goes down. Every time you have an inverse relationship, you get a curved line graph like this. And you know this from math. This keeps on going and going and going and never hits zero. So this is an inverse. Sometimes you guys call it an indirect relationship. This is more mathematically probably what you're going to hear most often. So when the volume goes up, the pressure goes down. When the pressure goes up, the volume goes down. So in this example, you've got this in your foldable. If a gas expands from a volume of 5 to 25 liters at an initial pressure of 3.5 atmospheres, what's the new pressure going to be? So I love to label, and I would love for you to label as well. So where it says 5 liters, that's going to be my volume 1. That was my initial volume. And then it went up to the 25 liters. That's my volume 2. The initial pressure, which means beginning. So there's my P1. We're looking for the new pressure. That is P2. So eventually we're going to go to our foldable, and we're going to have this thing full of 6 formulas. And we're going to go and find the one that has volume and pressure, and it's Boyle's law. So we say V1 P1 equals V2 P2, and that's in a different order than I gave you earlier. So it's the same thing. P1 V1 equals P2 V2. Just as long as you have your 1s and 2s on the correct side of the equal sign, everything works out. So we are looking for P2. So I'm going to put a box around P2. I need him to be by himself. So the guy that is ticking him off is this V2. V2 cannot be next to P2, so we have to get rid of him. You should recognize, because now you've been in Algebra 2 or Geometry for 6 months, these guys are being multiplied. So to get rid of him, I have to do the equal and opposite, which is divide both sides by V2. Again, we don't have like terms because we've got liters and we've got atmospheres, and so I can't plug my numbers in first and then solve. You really need to solve first. Plug your numbers in second. So now our new formula is P2 equals P1 V1 over V2. Now you can plug in your numbers. My pressure 1 was 3.5 atmospheres. My volume 1 was 5 liters. And my volume 2 was 25 liters. And you also know that I love to cross things out, so here it goes. Liters and liters cancels. Here's the deal. Sometimes maybe they had given you 50 milliliters. If they had given you 50 milliliters along with 25 liters, because these two units don't match, you would have had to have convert one of them. Did it matter which? Nope. I could have converted my 50 milliliters to liters or my 25 liters to milliliters. They just have to match. So you can do this cancel step down in the bottom right corner here. All right? If they don't match, you can't cancel, so you can't divide them. You've got to do something to make them match. So I put this in my calculator, and I end up with a new pressure reading of 0.7. If we wanted to do sig figs, we're looking pretty good because that 5 liters only had 1, and we only have 1. We put liters on that. Now, let's turn on your brain and use some common sense. Does this make sense? What happened to our container? Our container got huge. It went from 5 liters to 25 liters. So if my container is huge, what's going to happen to my number of collisions? It's going to be less. And if there's less collisions, there's less pressure, and the pressure went from 3.5 to 0.7. So that should make a lot of sense in your brain. All right, next. Oh, I thought this was pretty cool. I found this kid online. He said the increased pressure from the water decreased the bottle's gas volume. So the air on the surface of the ocean took up all, I don't know, 20 ounces of space in that bottle. But when he brought that same bottle of air down underneath the ocean, the pressure is so great, it pushes on that bottle and it makes the gas contract and get smaller. And so the pressure went up, the volume went down. That is Boyle's law. Without that air tank on his back, that's what would happen to his lungs. But with that air tank forcing that air into his body, it's forcing his lungs to inflate so they don't collapse and he doesn't die. All right, next guy, Charles's Law. And so we say, there used to be this old sitcom on TV, and I used to tell my kids, Charles in Charge is on TV. You guys have never heard of that. And so we say Charlie Brown is on TV. So temperature and volume is Charles's Law. Basically what's happening here is when things get hot, they expand. When things get cold, they shrink. And so basically the pressure is constant, so we don't talk about the pressure at all. The volume of a fixed mass of gas varies directly with its Kelvin temperature. Notice the word Kelvin here. You can't use Celsius, and we talked about that last week. If you put Celsius temperatures into these equations, they don't work. And so if you look at this lab data that a group collected over here, you'll notice that the temperature is going down, 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 down. It's getting very, very cold. Look what's happening to the volume. It's shrinking, it's shrinking, it's shrinking. You can go to Party City and you can buy some helium balloons and you can take them outside and put them in your car. And on the way to the party, the balloons are going to pop. Tell me what season it is outside. If the balloons are popping, the gas is expanding because the temperature is hot. So that means that it's probably summer. Now you can take the same balloons blown up by Party City, walk outside in January when we had the ice storm, and those balloons will actually contract and get smaller, and they will shrink. And so it almost looks like the air is leaking out, or the helium is leaking out of your balloon, and you're kind of miffed because you're like, man, I just paid money for these balloons and they're not blown up all the way. And then when you walk back into your party, because the room is warmer than the outside, they'll actually reinflate to their normal size. It's cool to watch. So you should try it with a freezer. Anyway, here's Charles's Law. V1 over T1 equals V2 over T2. So when the relationship is direct, there is a fraction. I despise fractions. We're not going to worry about the pressure because it's being held constant. We only care about the volume and temperature. Now, when I was in high school, Mr. Watts, God bless him, he said, we're not going to learn it in fraction form. We're going to cross multiply immediately. So when I learned this formula, the formula for me was V1 T2 equals V2 T1. So if you like that, go ahead and learn the linear version. It saves you a step later when you don't have to cross multiply and solve your variable and whatever. So I like putting it linear, personal preference, but in a textbook you would see it stacked as a fraction. So this is what a graph would look like of a direct relationship. Basically, when things get hot, the temperature goes up. That's going to inflate your balloon. When things get cold, the temperature goes down. That is going to make your balloon shrink. And so you get a straight line graph from a direct relationship. Remember, this is its Kelvin temperature, not Celsius. So if you look at my little graphic over here, the pressure gauge is staying the same. And so, unfortunately, my thermometer isn't looking too good. So if we looked at this first box here, because the volume is smaller, we can estimate that the temperature is lower than the other one over here because the box got bigger. So that gas expanded, meaning the temperature had to have been higher in that second box. Found a few pictures online. There's a little kid. He's in his kitchen, and he's got his balloon, and it's nice and big. He blew it up all the way. He took it outside, and you can definitely notice that the volume of the balloon was smaller. So here we've got some boiling water, expanding the gas, blowing up the balloon. Here we put it in an ice bath, and shrinkage. Absolutely. So when you jump in a pool, things shrink, if you know what I mean. So let's do an example real fast. So we've got 22.4 liters of oxygen, and it's heated from 23 degrees to 50 degrees. Let's label. It says, what's the new volume? So that's going to be my V2. Here's my V1. I've got my T1, my temperature 1, and I've got my temperature 2. Now, if you remember, we can't use these Celsius temperatures. So I'm going to come over here. I'm going to add 273. And I'm going to end up with 323 Kelvin. I'm going to do the same over here for my 23 degrees and end up with 296 Kelvin. So now I've got everything labeled. I've got my Celsius temperatures in Kelvin. Now I can write my formula. V1 over T1 equals V2 over T2. We are looking for the new volume, V2. So we can put a box around our variable. And now we have to get rid of T2. I totally think it's easier to cross multiply this. So I'm going to cross multiply and show you how to solve it this way. V1 T2 equals V2 T1. Put a box around your variable. Let me grab a marker here, which is V2. Now you have to get V2 by itself. So you divide both sides by T1. So now it's ready to go. Let me show you the other way. V1, V2, T1, T2. If you're looking for V2, some of you can already see that T2 is the problem. We've got to get rid of T2. Currently, he's in the denominator. So to get rid of him, I need to put him in the numerator. So I'm going to multiply both sides by T2. And so you end up with the same thing. V1 times T2 over T1. I don't care which way you do it, but you need to be good at one of those two ways. It was nice because V2 was in the numerator. If we were solving for T2 in the denominator, things get a little trickier, and that's when I would definitely cross multiply. So let's go ahead and plug in. So we've got V2 is equal to T2. Our second temperature was 323 Kelvin. That was our T2. Times our V1, our initial volume, was 22.4 liters. So it looks like we have a mole of gas here. We're going to divide that by T1, which was 296 Kelvin. My K's can cancel, so my answer is going to be in liters. So we plug that in our calculator, and we end up with 24.4 liters of oxygen. Ta-da! Again, we will go over what to do if you've got a number in the denominator when I see you again. But for now, see if you can figure it out. Use your algebra skills. All will be well in the world. Now we've got Avogadro's law. Looks a lot like Charles's law. It's a stacked relationship, only with different letters. Basically, the law says this. If you increase the number of moles, you've got to get a bigger container. Duh. So if I increase the number of particles, they're all not going to fit in that original container. So the volume is going to need to expand if the temperature is constant and the pressure is constant. So notice that P and T are nowhere to be found. And so we've got V1 over N1 equals V2 over N2. Again, it's a direct relationship, and so when one goes up, the other goes up. So it's a nice little straight line graph like this. So if you double the moles, you need to double the size of your container. If you triple your moles, you need to triple the size of your container. So let's do this example. We've got 4.65 liters, that's my V1, of carbon dioxide, and it increases from the original moles, which is N1 of 0.8, to 3.75 moles, which will be our N2. What's the new volume? V2. So we write our handy-dandy formula. V1 over N1 equals V2 over N2. Now we are solving for V2. Again, it's in the numerator, so it's not that hard to solve. I'm going to go ahead and do the cross multiply way. V1 N2 equals V2 N1. We're looking for V2, so we've got to get rid of the N1. V2 has to be isolated. So we come over here and we plug in. It's going to be V1 times N2 over N1. And the V1 was 4.65 liters. And the N2 was 3.75 moles. The N1 was 0.8 moles. Moles cancels out. We put it into our calculator, and our calculator says 21.8, which would be liters. But unfortunately, I gave you this horrible number with one significant digit, so I have to take that and round it to one significant figure, which is 20 liters of carbon dioxide. So there's Avogadro's law. Next, we have this guy with the unfortunate last name. His name is Gay-Lussac. It's kind of sad. Anyway, on the back of your foldable, we're going to add this guy's law because for some reason they left him off. I'm not really sure why, but this is the kind of fun one that you guys kind of like to talk about. Basically, what happens to the pressure when you make it really, really hot. So if you take an aerosol can and you put it in the fire, whoa, the pressure goes up, right? And so we're keeping the volume constant so it's not a factor. And you've got this pressure here, and it varies directly. So another straight line graph. So if we were to graph this, it would go up like this. Maybe the temperature is on this axis and the pressure is on this axis. And again, our temperature has to be in Kelvin. So the law, you need to write down the law, is P1 over T1 equals P2 over T2. I will caution you. Have I thrown an aerosol can into a fire? Yes. Did we all run away like little scaredy cats afterwards? Yes. Did it explode? Yes. Did we get in trouble at an 8th grade church camp? Yes. Anyway, so please be careful. Don't play with aerosol cans in fire. It is bad. So check out this little kid in the bottom corner. This is what happened to his face after the aerosol can blew up at his camp out with his buddies in his face. And luckily he didn't need a skin graft where they have to take the skin off of your inner thigh and peel it off and place it onto your face. But he did recover, but it was quite sad. He no longer has any freckles. Anyway, and there is a busted can up at the top after what happens to a can when you put it into the fire. And luckily, I don't think the kid had any shrapnel from the metal scratch his face. It was all 3rd-degree burns. Anyway, so here we go. We've got this aerosol can. It had an initial pressure of 5.5 atmospheres. So there's my P1. We're at 23 degrees, and that is our T1. We're going to go ahead and just automatically add 273. So there's our 296 Kelvin. So that's really our T1. When the can was heated over a flame, its contents heated up to 97 degrees. There's our T2. We're going to add 273. And get 370 K. Right before it explodes, what's the new pressure going to be? So we're looking for P2. So we've got to write down the law. P1 over T1 equals P2 over T2. We're looking for P2. If I'd been smart, I would have picked one with a variable in the bottom. And we're going to solve. Cross multiply. P1 T2. P2 T1. Looking for P2. Divide both sides by T1. Get that variable by itself. We're ready to plug in. Our initial pressure was 5.5 atmospheres. Our second temperature in Kelvin was 370 K. Our initial temperature was 296 K. Hopefully you can already see how easy it would be to flip these numbers around and put them in the wrong place or solve the equation wrong. So you just have to pay attention to details. I know you can do this. That's not the problem. The problem is you get in a rush, you don't think about logic or common sense, and you don't think about your answer making any kind of sense. So we'll look at that here in just a second. We put it all into our calculator, and we end up with 6.9, because I only need 2 sig figs, atmospheres. Now let's make sure that this makes sense. What happened to our temperature? It went from 23 to 97. And so that's a pretty big difference in temperature. So it got really, really hot. So look at our pressure. It went from 5.5 to 6.9. We're talking 7 times the normal atmospheric pressure here. That's a lot right before it explodes. And so that's why we don't want to put it into a flame and put our head right over the campfire. So that makes logical sense. My answer makes sense. We solved for the variable. We're going to keep trucking. If your brain doesn't hurt by now, you're not doing it right. Last but not least, we have the combined gas law. So basically, if I'm not holding anything constant, if I'm increasing the temperature, and when I increase the temperature, the volume changes, and when the volume changes, the pressure changes as well. Now you've got all of your variables changing at the same time. Typically, your number of moles is going to get kept constant. And so we don't talk about the number of moles in the combined gas law, but we indeed could put it in there if we really wanted to. And so it's just a way to take all 3 laws, and I really don't use Avogadro's law in this. I really just use the Gay-Lussac law with this guy. And we get one usable equation. And so it looks like this. And again, I typically don't use that. You can go ahead and write it on the flap. But if they don't give you any values for moles, you will literally just leave that out of the equation. So in theory, you don't need Boyle's law, Charles's law, Gay-Lussac's law, or Avogadro's law, because all 4 laws are staring at you right here. Check it out. P1V1 equals P2V2. There's Boyle's law. V1 over T1 equals V2 over T2. There's Charles's law. P1 over T1, P2 over T2. There's Gay-Lussac's law. And last but not least, V1 over N1, V2 over N2. There's Avogadro's law. They're all there with one law. So you could use this one law in any of those questions. And so if somebody said, hey, tell me what the new temperature is if the volume changes from here to here, and you're only using temperature and volume, your brain is literally going to go over here and say, well, pressure didn't get mentioned, moles didn't get mentioned, here's my formula. And you're going to move on. But we're actually going to do one right now where we are going to talk about the pressure. So we're going to keep him in there. Look at our example. A gas is cooled from 45 degrees to 20 degrees. So what happened? It went from here to here. It cooled off. It got colder. We're going to add our 273. And so for this 45, it ends up being 318 Kelvin. And for the 20, it ends up being 293 Kelvin. The pressure also changed from 103 to 101.3. So we're going from pressure 1 to pressure 2. This time they use kilopascals. And the volume, be careful of the wording here, settles to 16. So that's implying that that is your V2. That's what it ended up as. So look what they want. What was the initial volume? So we don't know V1. So we're going to write our formula. P1 V1 over T1 equals P2 V2 over T2. And I immediately cross multiply. I like them to be linear. So I end up with P1 V1 T2 equals P2 V2 T1. So in high school, the blue one is what I learned as the combined gas law because my teacher hated fractions and has brainwashed me to hate fractions as well. So now I'm going to put a box around my variable, which is V1. So how do I get V1 by himself? Who's making him mad? Well, some P1 and some T2. So the ones making him mad are the ones that we're going to divide and get rid of. P1, T2. What you do to one side, you do to the other. P1, T2. Everybody goes away. So we start plugging in. Our initial volume is equal to, if you want to, you can put little placeholders here so you can just plug your numbers in and not have to do as much critical thinking. You need P2, so you go find where you labeled it, 101.3 kPa. You need your V2, which is 16 liters, and your T1, which is 318 Kelvin. Now you need your P1 on the bottom, 103 kilopascals, and your T2 on the bottom, which is 293 K. Look what we can cancel out. Kilopascals goes away. Kelvin goes away. We're left with liters. We're going to slap that onto our answer at some point. And now we grab our calculator. Be careful when you type this into the calculator since you have two numbers down here in the denominator, just like when we do train tracks. Divide this guy by 103. Divide again by 293. Don't hit times in between those two numbers, or it's going to put the 293 in the numerator for you, and that's not what you want. So your final answer ends up being 17.1. 3 sig figs. Everybody's happy. They didn't tell us what the gas was, so we can't label the chemical. And that's about all. I am going to show you one example of what to do if it's in the denominator. So if I had a Charles's Law problem like this, and they wanted to solve it for T2, if you're trying to do the algebra instead of the cross multiply, at this point, you have to recognize that T2 is in the denominator, and you can't use him until he's in the numerator. So you have options. You could flip your entire equation over, and now solve for T2 by multiplying both sides by V2. Or you could do the algebra, which says you're going to multiply both sides by T2. Get rid of that. Now T2 is my variable, but now I've got to get rid of V1 and T1. So I've got to divide both sides by V1 to get rid of him. Multiply both sides by T1 to get rid of him. So I end up with the same thing as I did on the bottom. There's just a lot more work with this top one. That's why I don't do either one of those. Of course, I'm going to cross multiply. So I've got my T2 times my V1. And I've got my T1 times my V2. Since we're looking for T2, divide both sides by V1. I think it's faster. I think it's easier. There's less room for error if you just get in a routine and do it over and over. So you learned a little bit about shrinkage. You learned not to throw aerosol cans into a flame. And you learned that your little brother's head will explode with enough pressure. So have a great night. Sorry it took so long. And good luck on STAR this week. Bye.